Okay, we're recording. Talking about elementary functions and non-elementary functions, because I want to explain why it is that we are studying numerical integration techniques. Why are we going back to Riemann sums when we've learned the fundamental theorem of calculus? Like, why do we need to do Riemann sums? We can just find antiderivatives and plug some numbers in. Or can we? Well, here's the problem. Some functions don't have antiderivatives. Some elementary functions don't have elementary antiderivatives. And this is the problem. Okay, because if it doesn't have an antiderivative that is an elementary function, then how do you evaluate it? What is it? What the heck even is it if it's not one of these elementary functions? Okay, what is ERF? What is ERF of x? It's called the error function. We'll get to that in a second. And so yeah, if you can't find an antiderivative, then how do you apply the fundamental theorem of calculus? You can't. So an example of this is the function e to the power negative x squared. E to the power negative x squared is an elementary function. It's a composition of an exponential and a power function. No problem. It's elementary. It can be written in terms of these functions. But it doesn't have an elementary antiderivative. There is no antiderivative for this function that we can write down in terms of exponentials and logs and trigs and power functions and so on. The antiderivative of that is non-elementary. And it's related to this thing called the ERF function. These are related. So let's go to Wolfram alpha, and I'll show you where this comes up. You go to Wolfram alpha and say, what is the integral of e to the power negative x squared dx? It will tell you that the antiderivative of e to the negative x squared is, come on, Wolfram alpha, you can do it. I know you got to think hard about it. I know it's complicated, but I know you know it. I know you know this one. You got this. Where are you? What's going on, Wolfram alpha? Is it just my internet is slow right now? I'm trying to upload some videos in the background, and maybe that's the problem. Maybe I should pause that. Am I cutting in and out at all? Oh, actually, the videos are done uploading. The videos are fine. Let's just try this again. All right, Wolfram alpha, we'll give you another try. I wanted you to demonstrate this for me. There we go. Okay, I just had to reload the page. It's fine. So here's what it tells us. The integral of e to the negative x squared is this. It's a half times the square root of pi times ERF of x. What is ERF? ERF of x is the error function. Tell me about that. Tell me the definition of the error function. ERF looks like that. It's got this nice simple graph. You know, the graph looks perfectly fine. It's a nice continuous graph. But it's defined like this: error function of it's actually, okay, so this is actually, I think, the definition for a complex input. It works like this for real number inputs as well, but even if you want to do a complex input, it's defined on complex numbers too. But ERF of its input is 2 divided by the square root of pi, okay, times the integral from 0 to z, the input, of that function, e to the negative t squared dt. So like, okay, if the antiderivative of e to the negative x squared is defined in terms of that definite integral of e to the negative x squared, it's like, it's not like ERF isn't something that you can handle on its own, independent of this integral. ERF is the result of that integral. Okay. So so like if we want to evaluate ERF of 2 or whatever, we need to be able to evaluate a definite integral of e to the negative t squared from 0 to 2. But we can't evaluate that with an antiderivative because ERF is the antiderivative. Do you see how that's circular? So like, how do you even do it? Well, the way you do it is you just get a good approximation. You don't do it analytically. You don't find an antiderivative and use the fundamental theorem and to get the exact value. No. You just approximate that integral as best you can with a Riemann sum. So that is why we are studying Riemann sums right now. We're going back to Riemann sums because sometimes you have to go back to Riemann sums. There's some functions, and frankly, functions that are really important that you just can't integrate in the usual way. So I wonder if it says down here the applications of it. Is the erf function has some really important applications in probability. Does it tell us here? It has a lot of stuff on this page. It doesn't, but I will tell you. So you guys familiar with the bell curve? It's the standard distribution. Okay. Standard distribution from probability. It's this very important idea in probability / statistics, right? Very important concept. This bell curve is defined using e to the negative x squared. It's not exactly e to the negative x squared, but it's like defined using that. Like if you look at the graph of e to the negative x squared, that's what it is. It looks like a bell curve. The actual bell curve that they use in statistics and probability has a couple of extra parameters in there, like there's a square root of pi in there somewhere, that kind of thing. But if you graph e to the negative x squared, yeah, there it is the bell curve. And now probabilities are calculated by doing integrals of this thing and finding like the area under this curve, over, for an interval along the x-axis, that is the probability that the random variable falls into that range. So like, so like that shaded region there, like the area of that region is the probability of the random variable being between 0 and 1. So all this stuff about probabilities, it all comes back to integrating the bell curve, right? Integrating the bell curve function, which is defined using this non-elementary integral, right? So that's why this one in particular is really important, is because it's like crucial to probability and statistics. So that's one example of a non-elementary integral. There are others. Let me pull up this window here. There are others. There's a bunch of examples of non-elementary integrals. The error function is one of them right here, also called Gaussian integral, e to the negative x squared. But there's other things like 1 over the natural log of x, sine x over x, sine or cosine of x squared. Those are the Fresnel integrals. Those are important in something with physics. Let's see, it says down here something about diffraction phenomena. Fresnel diffraction phenomena are defined through these integrals. There's some physicsy thing that uses these Fresnel integrals. Yeah, there's a lot of them. There's a lot of these non-elementary integrals that come up just, in various places. So that's really the overall value of what we're talking about today. Okay. So let's go back over that thing I showed you yesterday about how to do Riemann sums in Desmos, and then I want to show you how to do it in Python. Because Python, you're more likely to actually use Python in the real world than you are Desmos. Desmos is great for learning, but it's not really like a professional tool. Okay, so on the D2L page, I have in content created a folder called links to cool stuff. I always like to have a links folder. That's where I put all my Desmos demonstrations. So this is the first time I've sent you a Desmos demonstration. So this is the demo that I did yesterday. So it starts with f of x. You can define whatever f of x you want here. So, like maybe square root of x or whatever, for example. Okay. And then you can change your x and your y, your a and your b. Let's take some values like this. Thank you, Diego. I was typing kind of fast, I guess. I spelled calculator wrong up there. We can change the number of n. And just like I showed you yesterday, we got n here. And so you can do 37 rectangles or whatever. We're calculating our change in x, which is called h here. And then we defined this function yesterday, g of I, which is the that is the it's the function that computes the sample points. xi star is the notation we used back in Calc1. So textbooks will use the xi star notation. I just, Desmos doesn't allow that kind of fancy notation, so it would just a function, g of I. So this is currently the right-hand endpoint function, and then we are summing the area of the rectangle, which is width times the function evaluated at the sample point, f of g of I. That's the area, width times height, and we're adding them up from the first to the nth subinterval. And that gives us a nice approximation of the integral. So we can see here, these are, this isn't exactly this. Of course, it's just an approximation. It does get better as we increase n. Let's take n all the way up to 100. It's better. It's pretty good, right? So what we're going to be looking at in this section is different ways of doing this, different ways of different basically schematics for calculating the area of these rectangles that can give you more accurate approximations. Okay, so how can we make this approximation as accurate as possible for small n without having to make n ridiculously huge? Because if you think about the fact that you're going to program a computer to calculate this, you want to have n be pretty small, because the bigger n is, the more work your computer has to do, the longer the program will take to obtain a sufficiently accurate approximation, right? So you want to be able to obtain accuracy with smaller values of n. Okay, so we want to try to we're going to study 3 different new methods that we haven't studied before for doing this that have varying degrees of accuracy. So the first one we want to do is the midpoint rule. It's called the midpoint rule for calculating areas. The idea for this one is for each of your little subintervals here, boop, 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 boop. There's some subintervals. Here's our A, here's our B. The idea here is we're going to select the midpoint of each of these subintervals, and that is where we will calculate the height of the function to define our rectangle. It's always the exact midpoint of each interval, giving us these nice rectangles. The idea is that selecting the midpoint should be better than selecting the right-hand endpoint of each interval. That the midpoint should give you some sort of an average between the two, right? The midpoint of the X interval should give you like, that's the idea there, okay? So how can we adjust our formula? So xi star, instead of doing a plus I delta x for that giving us a right-hand endpoint, instead of doing that, what you want to do is add delta x some number of times, but then you want to subtract it 1/2 of a time, right? So to get to the second sample point here, you would want to add delta x twice, but then subtract 1/2 of delta x to go backwards to the midpoint. So what we can do to adjust our formula here is just say add delta x I times and then subtract 1/2 of delta x, which we can combine together into a plus I minus 1/2 delta x, like that. Okay. And so now what we'll be doing is summing up I equals 1 to n f of a plus I minus 1/2 delta x times delta x. And that small change of just subtracting 1/2 in there takes us from right endpoints to midpoints. Pretty simple, right? Okay. So I think now let's go ahead and skip over. Let's go ahead and go over to Python, where we can where I can show you how to do this. Okay, there's going to be other rules coming up. We're going to do the trapezoid rule. Which is where, as you can guess, you have these sort of like trapezoid type shapes that you build, right? So like if your function gets really steep or curvy or whatever, you kind of like connect them with straight lines and you make trapezoids. And then we have one called Simpson's rule, which we'll get to another day. And Simpson's rule is this fancy thing where you're approximating with like parabolas. Okay. All right. So I want you to follow along with me. Go to online-python.com. I'll put a link in the chat for you guys. Then I'm going to try to get rid of my advertisement. Oh, I can't get rid of my advertisements. Let's try that again. onlinepython.com. So this is a nice, simple way to do some Python programming without having to download any fancy software or whatever. If you don't have any programming experience, don't worry about it. I'm never going to put this on like a quiz or anything. This is always going to be something that's sort of optional, okay? So if you never have any programming experience, if you don't have any at all, don't worry about it. Follow along with me today, okay? I'm going to show you how to do a little bit of programming, and I'll explain as best I can what we're doing. And maybe anybody else who has more programming experience than me, which is probably many of you, because I don't really have a ton of programming experience. Anyone else who wants to comment or chip in to the discussion of how we're doing this in Python should feel welcome to do so. I got to get my notes up on the other screen so that I don't mess this up. Hang on a second. There you go. Numerical integration in Python. Oh, I'm in the wrong place. Hang on, that's why. Here we go. Numerical integration in Python. Over there. Okay. So the first thing we're going to do is everybody at the website and you got your Python thing? We're all good? online-python.com. Okay. So the first thing you want to do is going to just delete everything from this file here. So this says main.py. This is going to be where we type our code. And then what we're going to do is we're going to click run, and all of the outputs are going to get spit out down here. Okay. So that. Okay. So now, first thing we want to do here, and you don't have to type exactly what I'm going to type. I'm going to type some comments, which in any programming language, you can type comments that are like not part of the code by using some sort of a special symbol to indicate that there's a comment. In Python, it is the pound sign, hashtag symbol, right? So I'm just going to put that in so that I can type in what I'm doing. So the first thing I'm going to do is define the function we wish to integrate. So for this example, I'm going to use x squared. And the way I'm going to do this is I'm going to define an actual function in Python. Now, in Python, if you want to define a function, you use the abbreviation DEF for define. And you can see it turns blue when you type DEF. And you want to make sure to just type it lowercase. Can you type define like that as well? I think I've always seen it like this with DEF like that, which will work fine. This means we're defining a function, and then what we're going to do is name the function. I am going to name it f of x like this. So what this means is the name of the function is going to be f. It's going to have an input, and the input of that function is called x. All familiar ideas from algebra. But then in Python, in order to define the function, you have to put a colon, okay, and then hit enter. Now, when you hit enter, whenever you do something with a colon and then hit enter, it's going to take you down, but down a line, but it's going to put a tab. Like, so now I'm indented. I guess indent is the right word, not tab, right? It's indented by some amount. That's very important. You got to make sure you're indented. Don't delete that indent, because Python is very, very picky about its indentation. So we are indented exactly one indent. Okay, so if you're over here, you can just hit tab to indent one step further. So we're over here, and in here, all I'm going to do is tell the program to return something. Return means like spit out an output. And what I'm going to have it do is return x squared. So whatever my input is, x, I'm going to use it here. And then the way to do squaring in Python is like times. It's like a double star. Single star is multiplying, double star is raising to a power. So x times 2. This means x squared. And then I'm going to hit return again, delete so that I'm back on the main indentation line. And now I'm done with that function. That function, you can you can collapse functions. So this is anytime you have a big block of code, you can like collapse it. And now whatever I type out here is going to be outside of that function. So the function is just done. It's done. So now we're going to define the interval a to b that we're going to be integrating over, and the number of steps, n. So that was a comment there. For this, we're just going to use some variables. So, Good question. Did I need a blank line? I did not. No, blank lines are I don't think ever necessary, but yeah, it's just sort of helps separate segments. So this makes it easier to read. Yep. So let's see. So I'm going to define a couple of variables here. So I'm going to have my left endpoint be 0 and my right endpoint be 2. So I'm going to be integrating from 0 to 2. Please feel free to choose anything else, whatever numbers you want. And for my number of rectangles, I'm going to go with 100. But you can pick any 0, any A, B, and N that you so choose. Okay. So now we're going to write a program to do the midpoint formula, to do a midpoint Riemann integral. Okay, so I'm going to we're going to define a new function to compute a Riemann sum using midpoints. Okay. Is it a little bit small? Is everything a little small? Maybe I could make it all a bit bigger. Hey, my ads went away. That's good. I got it big enough that the ads disappeared off the edges of the screen. So yeah, this is b equals 2. Correct. Thank you. The single equal sign here is what's called an assignment statement. We use that to specify, to like basically set the value of a variable equal to something. So now a, b, and n they're sort of variables, but like they're going to store these values. Go ahead. Is that Ali?
Yeah. Do you have to make the multiplication sign like almost the power?
No, if you want to choose a different function, you could do just 2x. Like this would be 2x, x times 2. This is x squared. I don't think that Python accepts that notation. Does anybody know if Python accepts the caret notation for exponents? Isa points out math.pow x comma 2. That works if we import the math library. I haven't bothered to do that. So that's why I suggested just x star star 2. By the way, I just chose x squared, or you can do x cubed or x to the 4th or whatever. But a power function like this is nice and easy because you don't need to import the math library to perform it. So that's why I chose something like that. Just so we wouldn't have to worry about importing libraries at all. So yeah, I guess, okay, let's go back. I'm doing x squared. Please feel free to do x to whatever power you want. You guys can do other things, and we'll see how it works. So, okay, we're going to define another function. So I'll do def, and then I'm just going to call the function midpoint. And this function needs some inputs. So this function is going to use the f of x function we defined up above, but I'm going to give it the inputs a, b, and n. So that it knows the left and right boundaries of the integral and the number of rectangles you want to use to approximate the value. So a, b, n, and then another colon, since we're defining a function, and now we're gonna type in our whole definition of the function inside here. I'm just gonna hit enter a few times to give myself some space so I can move it up a little bit. All right, so now how are we gonna define this? So what we're going to do is instead of doing exactly what's written down here, what I actually want to do is we're going to sort of keep a running value of the result. We're going to keep a running sort of sum. We're going to do like f of x1 star, and then we're going to add f of x2 star, and then we're going to add f of x3 star, and we're going to sort of carry on like that, where we're just adding up. This is going to be called an iterative method. we're going to have our index. We're going to use the index I, just like we did over here, and have it go from 1 to n. But we're going to be sort of having a variable called result, and we're just going to be adding on to that variable and updating the value of that variable every time you add on a new height. So basically, we're going to be adding up all of those heights first, and then when we're done adding up all the heights, then we're going to multiply the entire thing by the width. And the reason for that is because we can just factor out that width, right? And just kind of multiply it in at the end. Does that make sense? Adding up all the heights and then multiply the whole thing by delta x. That's going to be our approach here. So going back over to our code, I'm going to start by defining a new variable called result, and I'm going to set its initial value equal to 0. Oops, not 100, just 0. Sometimes, by the way, you'll notice that the sort of Python workspace we're using here wants to keep like it wants to guess what you mean to say, and then it wants to keep like what's this called? Like autofilling. Yeah, aggressive autofill. That's well said. Yeah, if you just type a space after everything, that's never going to cause a problem. Spaces aren't going to cause a problem in your code, but it does make that autofill go away. So before I hit enter to carriage return to the next line, I always get into the habit of just typing a space, and then autofill is disengaged and it doesn't mess you up. So result equals 0, just initializing that value. We're going to add on to that as we go. Now, the other thing we need to do is calculate that delta x, which we decided to call h. We called it h over in Desmos. I'm going to do the same thing here. So to calculate delta x, we do b minus a in parentheses, and then divided by n. And I do believe single division is going to work just fine right here. Can anyone with more Python experience confirm for me that all you need to do is single slash, not double slash? There's different types of division in Python, and I think we want just regular dividing. This is tricky because the other type of division is where it like rounds to the nearest whole number, and we really don't want it to do that, right? Because if we're using like 100 or 1,000 rectangles, we got to make sure that the width is like some like decimal approximation. You know, it's going to be like what's in what they call in programming like a floating point number, which is 0.00 blah 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 or whatever. Okay, thanks, Madison. So Madison has confirmed the double slash is where it rounds, or it rounds down. It's called integer division. So yeah, we're using a single slash for our division here. Okay, so right, so there's calculating the width. What do we do next? We want to plug in a we want to like calculate the x values. So like the xi star is basically what we're going to be doing here. We're going to do this in a slightly different way as well. It's not going to be a function like we did in Desmos. We're just going to simplify it a little bit and calculate the first sample point. And you'll notice, so that first sample point is going to be a plus plus a half of h. So like a plus h over 2. I don't know whether these, I had parentheses in my notes. I don't think they're necessary, but I'm going to put them in there just in case. So a plus a half of our h is like, that's just starting at the left endpoint and adding half of your delta x. So that's going to put us here. This is x1 star. Now, the simplified version of this is every time we like increment our index from 1 to 2, and then from 2 up to 3, and so on, every time we make our index go a little bit bigger, what we can do is just add an entire delta x to get to the next midpoint. See how that's going to be nice and simple? So instead of using this formula I came up with where we add a little negative a half here, we're just going to do the half right away, and then add the entire delta x every time. So that's a little simplification. All right, so how are we going to do this incrementing? We're going to go from I equals 1 up to n using what's called a for loop. So we're going to go for I from 1 to n. I think that works. Colon. There's another way to do this with a range, but I believe if I go from 1 to n, I believe it remind me, programming people, is it going to equal n or is it not going to equal n? Like, is it gonna do n or is it gonna stop at n minus 1? This will leave out n. Programming languages, by the way, are very picky about indexing. This thing about labeling like 0, 1, 2, or not labeling so much, but like keeping track of like the first, the second, the third. Most programming languages default to starting at 0 and going up to n minus 1. That's kind of like the other way. What I actually have written in my notes here is for I in range n, which if you type in range n, this gives I values from 0 to n minus 1. What I'm trying to do for you guys is go from 1 to n, because that's what we were doing. That's more familiar in math, but it's just kind of maybe now that I'm explaining it, we'll just do it the programming way. We'll go ahead and do this. So we're going to have to make a small adjustment to our formulas so that well, actually not much really, but we're going to have to make a small adjustment just to make it so that it accommodates the fact that our I goes from 0 to n minus 1 instead of 1 to n. Not really going to matter for this one actually, but it's going to matter more for the later, like the trapezoid rule. Okay, so this is going to be at least the correct number of iterations as I goes from 0 to n minus 1. And then every time that we go through, what we're going to do is take the result that we're keeping track of and add to it the function, evaluate it at whatever x currently equals. Okay. Now I used a little notation here, which is a nice little shorthand, common in a lot of languages. It's plus equals. This is equivalent to saying, like, add on to the value you already have and then update the value. It's equivalent to saying this: result equals result plus f of x. It's like the previous value plus the new value. Store that in the variable name so that it gets updated. Okay. So again, shorthand is just plus equals. So we've done that. We've updated the result, and then the other thing we need to do is take our sample point here and push it one step down the line so that it goes to the next point. So to do that, we're just going to take x, whatever it used to be equal to, and plus equals again, add on to it an h, which is the width, right? And that's about it. So result plus equals f of x and x plus equals h. This is going to add on the height and then shift the sample point down to the next rectangle. Repeat, add on the height, shift the sample point down, repeat, add on the height, shift the sample point down. And it's going to do that n times from 0. Basically, I goes from 0 to n minus 1. So yeah, there we go. That is it. So now we're going to, that's the end of the for loop. When you hit enter here, it might be on the same tab, but you got to delete it and go back. We should now be on the same tab line that we were for our function. Now, the very last thing we need to do for our function is return something. And the thing we want to return is not the result, but the result times h. Because remember, we need to take the sum of all the heights and multiply through by the width, distributing the width across and getting all the areas. So Nope. Let's spell return correctly. Obviously, it's very picky about spelling. There we go. Cool. So now I can get out here, and that function is now done, right? This function is complete. I can, it does its thing and it returns the result. Now let's see if it works. What I want to do is print midpoint rule colon space. And I put that in quotes so that it's going to print exactly those words. This is what it's going to print out to the screen when I run the program. And then I'll put a comma. And then I want it to print out a number. And the number is going to be whatever the midpoint function spits out. So I'm going to do midpoint A, B, N. So I am taking the specified A, B, and N values up here. Those are getting plugged into the midpoint function for the A, B, and N that it calls for there. And then it's going to spit out a number. So let's print it, or sorry, let's run the whole program and see if it works. Run it. It gave me 2.66666 zeros and then a 3. Let's see if that's right. Let's see how good that is. So what are we doing? I'm doing x squared from 0 to 2. If it's x squared from 0 to 2, using 100 rectangles, it should give me, yep. Well, actually, oh no, this is, I got the, there we go, 0.6666. 2.6666. Yeah, that's good. And the actual value of the integral is 2 2/3. So it's doing a pretty good job. It's doing a pretty good job of approximating that 2 2/3 for us. Yeah. Now there is a question. So just clarifying the thing about the range. What we want to do is you can either say range n, which would go from 0 to n minus 1. The number of steps is n. If you start at 0, you go to n minus 1. The number of steps is what matters most. If you want to do 1 to n, what you actually have to do is 1 comma n plus 1. So it always starts at this value and then ends as soon as it gets to this value. But that means that it doesn't actually use that value. It stops one short. So this would go from 1 to n. But it doesn't really matter for this one because all it's doing is keeping track of the number of times it does it. And that just needs to be n. That'll matter more when we do the trapezoid rule tomorrow. So, all right. So I hope you've enjoyed this this little exploration of Python and how to write a Python program to do a midpoint rule. Now we can use this. You guys are welcome to use this on this exercise set that's due Friday. Tomorrow, I will show you how the trapezoid rule and Simpson rule work. Then you can do those too. Bye, everyone.
Tristan.
What's up, Ellie?